Guys, now we are on live.
Good evening, everyone, and happy Independence Day. I am Aditya Jyotipal, and today I will be talking to all of you about machine learning and especially computer vision. This talk is mainly targeted at beginners, and we would be starting from the ground up. Starting off, I'll take a few moments to introduce myself. I am a Google Experimental Facilitator. I'm the team lead and co-founder of Cognitive Applications Research Lab. These are some of the organizations I've had the fortune of working with, like Samsung Research, GirlScript, Google, and I'm also an ambassador for Pi and AI, Deep Learning Pi and AI event. So swiftly moving on, let's discuss about what is machine learning. Like, what do people think like when they talk about machine learning? Whenever I ask this question, we always get answers like machine learning is when machines learn from themselves or when machines take decisions by themselves. But that's not a very sufficient answer, I would say. So how do we answer this in a proper way? One way would be, yeah. So one way would be writing that they make useful predictions by collecting the data and also the labels associated with that. So that is something which we often call as supervised learning. We also have something called unsupervised learning in which we just give data. Now, why do we say that just the definition that a machine learning by itself or a machine taking some decisions by itself is not machine learning? The reason is that we also have something called a rule-based approach in which a human programmer would be actually writing some rules. Like if you see a certain object, then if you see a certain pattern, then this object is present in the image. But that is not machine learning. That is something which you could call a rule-based system or an expert system. Uh, on the screen, you see the word pattern matching in red. Machine learning is basically pattern matching or glorified pattern matching. Uh, we try to find out some patterns in the image, or we try to find out some patterns in the data. It could be any sort of data. It could be images, it could be speech data, it could be X-ray scans, it could even be certain 3D patterns in a geodesic data. So any sort of patterns with its label, when we match them, it's called machine learning. Let's go on to today's agenda. Today we are going to actually start off with a brief description about what machine learning is, how it works, then talk a bit about image classification. Then we are going to do some hands-on demos with transfer learning for image classification. And finally, we are also going to see a very simple image classifier network and try to understand how this classifier works under the hood using a framework called Keras TensorFlow. So machine learning broadly classified as supervised and unsupervised. There's also something called semi-supervised, which I'll come to shortly. Firstly, let's look at supervised, in which the model is trained with labeled data. What do you mean by labeled data? So on the bottom right of your screen, you see the stop sign 1, stop sign 2, and all the labels with them. So we have not just the logos, but also the labels. On the right, we have just the logos. So to an unsupervised learning algorithm, it would probably call the first two logos which you have as one class and the second as another class. Class or cluster. Maybe cluster would be a better word. Now, in semi-supervised learning, what you do is you might manually want to label a part of your unlabeled data set, or maybe you initially do some unlabeled training, and then the human would label parts of that unlabeled data sets. For example, once the first two shapes or the first two logos from your unsupervised data set has been clustered into one, you could maybe call them as a triangular logos and the other one as a, how many sides does that have? Yeah, an octagonal logo. So that would be an example of semi-supervised learning. Moving on, let's see where we often hear like machine learning is an a broader class. Deep learning is a special part of machine learning. uh, there are a lot of ways these are defined, and we need not go much into a detail because it's highly opinion based. But Some of the strict definitions here are artificial intelligence is that domain or thing in which a machine would take any decision smartly on its own. Now we have a lot of classes within AI. For example, you have reinforcement learning, you have expert systems where you write the rules down, or even expert systems can be when they decide the rules on their own. That's also there. Now we have a special class of AI, which is called machine learning, in which you would be feeding the data and the labels. Other than that, you have something called deep learning. Deep learning is just machine learning, the same neural networks that you have in machine learning, just with a more number of layers and neurons. Also, there is a group of people who might think like, or one school of thought which proclaims that machine learning is purely statistics and deep learning is the use of computer science with statistics. That's very vague and does not really make much sense. Moving on, let's see how machine learning works with big data algorithms and technologies. So the one of the main things which you need for machine learning is a lot of data. And how do you work with a lot of data? With the big data tools like Apache Spark, etc. You need smart algorithms to make sure that your algorithm works efficiently and your deployment scales properly. And technology, obviously, because machine learning won't survive without technology. Like we use all these frameworks, we have programming languages to code the algorithms, etc. So what are things that machine learning can do? One of the things is classification, then we have regression, we have clustering, we have sequence prediction, and style transfer. So let's go over them one by one. So firstly, we see that in the first image, there are some blue dots and we have some red dots. Now, given any dot that a user makes on this image, you have to basically classify if it's in the blue class or in the red class. How do we do that? We draw a line of separation. And whenever we are trying to separate between two classes, we call it binary classification. In the second image, we have something, and in the first example, when I said binary classification, we could also have, say, 3 colored dots or 4 colored dots, and then we would have multi-class classification. But in the second image, that's actually more interesting because in this one, we have one single object, there's a lion, classified as 3 separate classes, which is a lion, a wildlife, and a mammal. So in this case, the specific thing here is that the same object is both the lion, a wildlife, and a mammal. Maybe the algorithm predicts with the lion with maybe 90% accuracy, and the wildlife 90% not accuracy, confidence. 90% confidence, maybe 6% for wildlife, so and maybe 3% for mammal, and maybe the remaining all the thousands of classes which we are training for, those all add up to 1% because the complete confidence measures have to add up to 100% for any output. Now, other than classification, we have something called regression. So imagine we have some x coordinates and some y coordinates. And for any value of x, we are basically trying to predict the value of y. So we definitely want to draw a best fit line through it. How do we draw this best fit line? We try to minimize the residual sum of squares. So what does that mean? For every single point in my screen, you see that there is a orange line dropping onto the line of best fit, right? So that's the difference between the predicted value for that x and the actual value, which is the blue dot. So we take these values and we square them, and then we add all the square differences. In the below example, you see that there are two points on the map, and we are basically trying to figure out how much time or how much money it would take to travel from point A to point B. Now, definitely we won't be traveling in a straight line, but even without that, we are basically trying to figure out the distance and associate it with the price point or the time value for that route. Now, one interesting thing is how do you decide if your problem is a regression problem or a classification problem? It can be either of them basically. See, in the regression, We have a continuous set of outputs. In classification, we have discretized set of outputs. For example, in classes, we have class A or class B. Now, instead of predicting the time as a continuous output, we could also predict that as, just give me, you could also predict that as, say, rupees 100 to rupees 110, rupees 110 to 120, 120 to 130. And then if you have 10 classes between 100 and 200, then you can actually reformulate your regression problem as a classification problem. Why might you want to do that? For example, imagine you have a company like Uber, and you give your customer a fare estimate of, say, 56 rupees, but then the customer's actual fare turns out to be 65 rupees. The customer might be unhappy, right? Because they're paying money more than the fare estimate. But if you instead give the customer a range like 55 to 65, then the customer might actually turn out to be happy because he's paying 2 rupees less than the maximum fare estimate. So these are the various cases where a regression problem might be reformulated into a classification problem. And similarly, in a classification problem, you can actually make the classes thinner and thinner and thinner, provided you have enough data that it simulates a regression problem as well. So that's enough about regression and classification. These were both supervised learning algorithms. Now let's talk about one unsupervised learning algorithm called clustering. In this data set, actually on my screen, it might not be very visible to all of you, but it's on the MNIST data set. And we have all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. We have these 100 digits from, excuse me, we have these handwritten digits from many users all over the world, and they have written multiple of these digits as well. So our goal here is to feed this data to a machine learning algorithm, and the algorithm has to separate them, preferably into 10 classes because there are 10 digits. Now, how do we know we have to use 10? Because even suppose it's a huge data set and we do not actually know how many clusters are there. Well, we don't. We actually try out for quite a few values, like we try out with 2, we try out with 10, 15, 100, etc. Anyway, for only 10 classes, it's very easy, and definitely before actually doing this in practice, a human would sit and look at the data and try to find out what the approximate number of classes are. But for algorithms where, for clustering algorithms, when we have, say, over 500 classes, it becomes a bit tough for a human to do. So in those cases, what is usually done is we try to use various cluster sizes and try to see where it's performing well. For example, the human 7 and 2 might look a bit similar. The humans 9s and 1s might look a bit similar. So even those clusters would be situated a bit close by. And we basically expect all the ones to be absolutely close by, all the ones to be very close by. The conditions for defining a good cluster is that very high intra-class similarity, which means that all the objects within the cluster should be very closely similar, and low inter-class similarity, which means that uh, the objects in one cluster should not be very close to the objects in another cluster. So let's look at the next task we can do, which is sequence prediction. What this means is that, say you have a sequence of data, like I buy, for example, how could I give you an example of sequence prediction? Okay, for example, say you want to make tea. What do? You get a bowl, you put in some milk, you add some tea leaves, you add some sugar, you heat it. So that's one sequence. So given the first 4 steps, and without knowing what your actual goal is, the machine should be able to predict the next step, because these are well-known steps and everyone makes tea more or less in the same way. Similarly, if I'm trying to type a word, for example, the word could be dinosaur. So once I move my fingers over the keys DINOS, the rest should be pretty much understood by the keyboard and it should predict it to me. So that's how Swift key or Google keyboard works. Sequence prediction actually has a lot more interesting use cases, like predicting what user would buy after buying a certain number of items, or for music releases. and much more, which we will be discussing very soon. Now let's look at something called style transfer. Uh, Previously, whenever I use it in sessions, I used to hear that style transfer is basically someone clicks a picture and you convert that picture into the style of some other artist, and you show the information from the first picture in the style of the art from the artist. But that's one use case of style transfer. Just a better way of how I would like to explain it is that, say you have some information which you wish to convey to someone, and you, every individual has a different way of expressing themselves. So you express the same information the way someone else would. When you do that, that is what I would call style transfer. For example, in Bengali, I could say "Ami bhat khai," and that basically would mean I eat rice. So keeping the information constant, if you change the way it's expressed, maybe through a language, maybe in form of art, maybe in form of a sound wave, or maybe even across mediums. For example, your input is an audio and your output is a label, like a textual label. That could also be style transfer. That one example of that would be video captioning. So in the second example here, we have EN male, which is probably trying to say something in EN female's voice tones, and JP male is the integration of the above two. This is the information from EN male in the style of EN female. Alright, so I hope style transfer is clear. By the way, since it's YouTube live, I actually cannot get your questions at the moment. But if you have any doubts, feel free to put your questions in the chat section so that someone from the organizers can get back to me, and I would definitely try to answer all your questions in the last 10-15 minutes of this workshop. So let's take a brief moment to discuss what the different types of machine learning algorithms we just discussed and how we can apply them. So recommending what someone will download based on previous purchases. All of these can be actually done in various ways. For example, we could use clustering, we could use sequence prediction. Clustering is like if someone's buying a lot of objects from the same cluster, maybe we could recommend some more objects from that cluster. What we could also do is we could analyze. So the person has bought A, B, and C, and we could analyze what other customers who bought A, B, and then C bought. So we are basically filling up D. So sequence prediction seems to be a way to go in this case. Let's look at the answer, and it is sequence prediction. Labeling email as spam or not spam. Again, multiple answers can be there. So if you're trying to give your output as a continuous metric, like give each email a score, say 0% or 10%. Say I'm 99% confident it's spam or 60% confident it's spam. Then that would be a regression problem. But if you are giving it binary output, like it is spam or it is not spam. If your output is binary, in that case, it would definitely be a classification problem. Since your question makes it look like it's a binary problem, probably the answer is classification. Captioning of a video. Video captioning can again be done via clustering. So you make those clusters and you try to label a few images from the clusters, and then from the labels which you have got, that's the words which you have collected, you can try to form a sentence. That could be one way. The other way would definitely be to analyze the video, whatever the video is trying to express, and then try to reformulate it in the form of text. So while explaining style transfer, I already explained this, how information from one form could be expressed in another form, and that would be an example of style transfer. Predicting the strength of a password. So now let us assume that we have some password and we're trying to predict it similarly in give it a score, like it satisfies 6 rules out of 10, so it's 60% strong. That would be a regression problem. But if you give it as if you try to give the strength in form of classes like weak, very weak, strong, very strong, mediocre, etc., that would again be classification. So it's both classification and regression, as I explained. Identifying famous landmarks in a photo is very simply put, uh, classification problem because you are just identifying that this object is there. For example, the Eiffel Tower is there. We have seen many images of Eiffel Tower before, so it's a classification problem. All right, suggesting spelling corrections, and that would be all right. So let's take a moment here to analyze what options we have. So imagine you are trying to suggest some spelling corrections. Would it be regression? Definitely not. Would it be sequence prediction? Some people might say yes, but see here we are actually not trying to predict the next alphabet as we are typing. The word has already been typed, and we are trying to after the complete word has been typed, maybe misspelled. We are trying to predict that okay, this is the wrong word and we have to correct it. So firstly, we'll definitely be consulting a dictionary to see if the word exists or not. If the word does not exist, we intend to give the nearest similar word. So assuming this dictionary is written down in form of clusters, we could very easily find out the simplest word or the closest word from amongst those clusters. Could it be style transfer? No. And could it be classification? Again, for checking that if it's a correct word or not, it's classification. But for suggesting the actual correction, no, it can't be classification. It has to be clustering. Predicting the quality score of an advertisement, whenever you're predicting a continuous score, it's always a regression problem. And translating between two languages, as I've already explained, keeping the information same, you're just changing the way you're expressing yourself, that is style transfer. So in the past 25 minutes, I think we have discussed what is machine learning. We discussed very briefly about what a rule-based approach is, in which the engineers actually write down all the rules, and improvements can only come from when the rule is actually changed. And it's not possible to identify, excuse me, it's not possible to identify real world objects with a rule based approach because, for example, if you want to identify a dog, you have to write down so many rules, maybe over thousands of rules, and that's not really feasible. So we take advantage of machine learning's pattern matching abilities, and we try to find out similar patterns from a data set and use it for machine learning. So when do we use a machine learning based approach? When we have a lot of data and when rules are complicated. And when do we use a rule based approach? When the rules are very simple to use. Then we discuss a bit about implementation, about when to use which algorithm. We discussed the differences between AI, machine learning, and deep learning. We did not really go much into history of ML, which we will cover, and then we discuss types of machine learning. Right now, for doing image classification, which our goal today is, we have to use an algorithm in machine learning, which we call neural networks. Neural networks are basically just used for finding patterns in your data. So, for example, let us imagine that you have a cat. In this, let's look at the few next slides. Um, all right. So in the first few layers, we'd be detecting maybe the ears of the cat, or actually in the first few layers, we detect very primitive features like edges, we detect diagonals, shades of color, etc., gradients of color, and then we try to form more bigger features which humans would recognize, maybe the ears of the cat or the dog, or etc. Various specific marks which a cat or a dog might have, eye shapes, etc. Those would be in the first 3 or 4 neurons, neural layers. In the last few layers, you would actually have complete faces of cats and dogs emerging. And those would be what you could call the average idea of what a cat is or what a dog is. Once we have that, we basically uh, would analyze those figures to understand that, okay, so this image, the input image, is most similar to this cat or this dog. To understand this in a greater detail, we'll look at how neural networks work. So each neural network has something called a single perceptron. And what a perceptron does is that it takes some inputs, and inside that it has an activation function. If the function is activated with that input, then yes, the neuron would be activated and some signal would be sent to the next neuron. Otherwise, this neuron won't be activated and a zero value would be sent to the next neuron. So for example, let's have the input 5. If our activation function is less than 10, so yeah, it's true. And the neuron will be activated. Otherwise, it won't be. So does 7 have a curve? No, it's just two straight lines. So we don't activate the neuron. But in this figure, does it have a curve? Yes, it does. So we activate the neuron. So we discussed activation functions like less than 10, but definitely that's not something we would be using for a neural network. Some activation functions which we actually use are sigmoid, tanh, and ReLU activation functions. Sigmoid is a very old activation function. It gives you a weighted value between 0 and 1, which is the actual probability as well. In ReLU, it's a smooth function between in the range of non-inclusive 0 to positive infinity, and from non-inclusive 0 to negative infinity, the value is 0. We also have some other variations of the ReLU activation function, like leaky ReLU, P ReLU, or E ReLU, which you can know more in the later parts. All right, so we are having some good questions as well. But before that, as I was mentioning, we have various types of activation functions like ReLU, like P-ReLU, exponential ReLU, or leaky ReLU, so which you can read upon later on. So now we have one question from Surit Datta, which says, can you suggest some ML methods for spelling correction other than autocorrect? What I would like to say here is that autocorrect is basically a vague term. It does use a lot of different machine learning methods underneath. For example, when I was working on spelling correction, I had a project in which I actually worked on spelling correction itself. So what our task was that we initially used the NLTK corpus to find out which words were not actually correct words. Then we used something called BERT, which is a bidirectional encoder representation, and we used those BERT uh, embeddings uh, to how do I put this? In BERT is actually a language model. It has a lot of values, like it has a lot of embeddings, like these are correct values, these are incorrect values, and the language model is also responsible for telling you which words or which phrases come together or what does not come together. So we use BERT LM to actually figure out from the rest of the sentence as well uh, what word would be most suitable, and we got some suggestions. And we also use the dictionary approach, like just which is simple clustering. So for example, if I have a word called APLE, then the dictionary might suggest APLET, applet, or it might suggest APPLE. So I get two suggestions from my dictionary or clustering, which is APLET and APLE. Now I use BERT. Now I have a complete sentence like, for my morning breakfast, I had an APLE. So this was what I had written. But BERT already knows that for morning breakfast, you would be having an apple, not applet. So we actually got a very, very high accuracy using that approach. And that is also something similar to what many modern techniques use as well. So another thing which you might have noticed from this explanation is that uh, when you deploy a machine learning approach or machine learning solution, it's hardly ever one algorithm. It's usually the problem is broken down or chunked into many smaller problems, and machine learning is used to solve all those chunks individually. RT has asked why cell transfer. Uh, I do not actually get at which point you asked this question. So I try to give you a brief explanation of the various use cases for style transfer. So one use case could definitely be a speech translation. So maybe from a French to German. You translate something. That could be an example of style transfer. Or you have an image and you want to draw it in someone else's style. So you click a photograph and you want to make it look like Picasso drew the photograph. So that would also be an example of style transfer. I think RT also says, I think style transfer is coding change. I'm sorry, I don't completely understand what you mean. Maybe you could rephrase your question and I could get back to you after this. Till then, we have discussed activation functions, not letting go of the main flow of the workshop. Let's move on. Uh, for doing style transfer, we do need to understand a little bit of Python and a little bit of TensorFlow. Without that, we cannot actually understand the demo, but don't worry if you're just a beginner. I will go through each line of code as well. So I hope my screen is visible to all of you. As just give me a moment as I set the runtime type and everything. So,
It's visible.
all right. Excuse me. So in this notebook, what we're going to do is we're initially going to download our data set, which is going to be a cats versus dogs data set, a very simple machine learning problem. Although it would be interesting to note that in 2016, this was one of the toughest challenges in Kaggle, and researchers were trying to still solve it. So here you can see that I'm initially installing TensorFlow, and then I would be importing the libraries matplotlib for plotting, NumPy for some numerical processing, OS for the OS level manipulation tasks, and then I'd be importing it and importing TensorFlow. And here you see something called image dataset from directory. This is actually a very neat way which Keras supports this. So imagine you have a directory called cats, and inside that you have many images like cat 1, cat 2, cat 3, cat 1 billion or something. So you do not have to label these cats and dogs separately. Keras will automatically infer the labels based on the directory name, which definitely makes the coding much easier because we don't have to write the labels separately or have to manually import them from a CSV, etc. So you see that I downloaded the zip here, and is my screen clearly visible, or should I zoom in a bit? I hope the text on my screen is clearly visible. Anyway, so what we have done here is that you see the part I'm highlighting right now, image dataset from directory. What we do is we are giving a train directory which has both the cats and the dogs, and we write shuffle is equal to true, and we write batch size is equal to batch size, which has been previously defined to be 32. So every batch we see 32 images of both cats and dogs, and try to improve our neural network in a by taking a particular step. And definitely we have image sizes of various size images in our data set, but we cannot actually train a neural network based on images of varying size. The reason is that uh, you have to your neural network's input has a constant dimension. Now imagine if at test time you give a random size input, then your neural network does not really know how to map those inputs or what sort of operations to do, what sort of math to use in the neural network. So we have actually rescaled every image to 160 cross 160. And that's actually done when you write image size is equal to img size in this method. It'll automatically rescale your images as well. So we also create a validation dataset, which is from the validation directory. And we write the class names as train dataset of class names. So we initially defined a train dataset as here. And in TensorFlow, whenever you create a dataset object, it also has a lot of attributes with it. for example, class names, etc. So with class names, you can get all the class names like uh, cat, dog, etc. Here you will have only two class names anyway. So here, when I run this cell, you can see for image comma labels in train dataset dot take one. What does take one do? It takes basically one batch. Wait, give me a second. So we create this plt.figure, and this will keep iterating over your batch to collect a lot of images of both cats and dogs. Or am I right? Yeah, it will go over the image for both cats and dogs, and it will convert the images to numpy and set the type as uint8, which is unsigned integer 8. It's setting the labels as well here, and it removes those small ticks which you have in the x and y axis because we don't need that. And so it shows you the image and the label, and for I in the range 9. And here you can also change this entire thing which you see, the 9 cats here, is one figure, and that figure size is 10, 10. So if you want all the cats or dogs to become bigger or smaller, you can change the figure size at the top. All right, we have not even reached into the main bulk of the code yet. So as the original data set is, yeah. So here we were, as the original dataset contains the test set, does not contain the test set, so we will be creating one. So what we do is we basically create a separate validation dataset with df.data.experimental.cardinality. What see we here this whenever you see something called dot experimental dot cardinality or dot experimental dot something, what it means is this is a new feature, and it would later on probably become tf dot data dot cardinality. They would drop the dot experimental part of it, and you basically pass in your entire validation dataset, and you get the validation batches out of it. Out of that, you then take 1/5 of it, or 20%. Whenever you divide by 5, you basically get 20%. So you create a test dataset from your validation dataset. Perfect. So we have basically split our dataset into a training set, and 80% of the validation set is still the validation set, and the rest 20% of it is the test set. All right, we can also count the number of validation and test batches now, which you see at 21 and 5, which is pretty good. Auto tune. These are actually quite advanced methods which we are using in this library here. You may or may not want to use this. For example, buffer size is equal to auto tune. This is again a TensorFlow Keras experimental feature which will improve performance. What basically it does is it prefetches your images instead of reading the data from the hard disk when you are running the algorithm, which should speed up your algorithm, which should speed up the training process. But even if you do not completely understand all this right now, it's completely fine. Even if you do not use this for your running in your particular case, that will also work out pretty well. So we will be using some data augmentation. Now, whenever we talk about data augmentation, people actually always do augmentation in two ways. One of them is called pre-processing, in which they might take various crops of the data set, or they might cut out parts of the data set, or blur the image, rotate the image, etc. All that's called pre-processing. Also, there's something called on the go data augmentation, which we would probably be doing here. I'm not sure if that's what they are doing here. Let me read this part once. Yeah, they are actually. So data augmentation has been made into two layers in your neural network before your initial layer. So what it's doing is it will randomly flip the image horizontally, not vertically, because you would rarely get images of upside down cats in your test data set. This is an assumption they are making. No, also we have a random rotation of about 20%. And make sure you know that these layers are only active during training, like when you call model.fit. Some other layers which are also only active during training are dropout layers and batch norm layers, for those of you who know about that. If you do not, we would probably be discussing that in a bit more detail if you get time. Otherwise, I would really encourage you to read up more on dropout and batch norm layers after this presentation. So here you see we have used underscore operator. What basically the underscore operator does is that it drops whatever was there. For example, whenever you do a train data set or take one, you will get an image and a label. You are not even interested in seeing the label, so you basically just drop the label. And we are implementing this augmentation and see how the same image is augmented in space. All right. Now what we will do is we'll have to rescale these pixel values, and we have to rescale them with the statistics of the rescale them with the statistics of the data set which has been used for this transfer learning. So what happens in transfer learning? Let's go back to my previous slide. So companies like Google and Facebook, they have trained huge neural network architectures on some source data, which again is huge, which has like 70 billion or 100 billion examples, training examples. And these algorithms, or these models rather, are capable of recognizing a lot of classes. Before that also, we had a lot of good data sets like Pascal, Walk, etc. But the modern data sets are truly enormous. So instead of, if you are given a task, so like identify a cat versus dog, one of the fastest ways to get coding or getting results is taking one of those source models from their code and dropping the last layer where they're actually predicting the 100 classes and adding a classification head for just the two classes, and you can basically get a good accuracy very soon. So this is exactly what we will be doing here. We'll be using MobileNet version 2. And as we discuss this, I'll tell you what are the do's and don'ts of using these transfer learning architectures. And then we'll also see how we can fine tune that architecture even better to get a greater level of accuracy. So let's get back to the code right now. So here there's some pre-processing which is being done with the MobileNet V2 statistics. If you want to know more about how these statistics work, so initially, see, you have to convert all your values between -1 and +1. So your pixel values will be from 0 to 255 because these are color images. There would be three channels. All of the channels have to be rescaled to -1 to +1. So you have a pre-processing function from Keras itself, uh, and we will be using the statistics. I have repeated this phrase quite a lot of time, like mobile net statistics, image net statistics, etc. To know more about this, you can always Google this up. The reason why we have to do this is because the previous architecture had been trained on images using images of a certain type, which is certain pre-processing. If your images are not pre-processed the same way, well, that architecture won't be able to perform very well. And here the statistics is very simple. It's just rescaling 0 to 255 to -1 to +1. Sometimes when you're using ImageNet in place of MobileNet, you have to use the mean and the standard deviation values. And those values are something which, well, aren't that simple. And hence we have another method called keras.applications.imagenet.preprocess input, I think, which you have to use. I, however, always recommend that you do not try to implement these pre-processing steps yourself, and always use a method if one exists for that dataset which you're using. Well, if one does not exist, then you have to go through their code and try to exactly use that pre-processing method. So we have we initially will be creating the base model from the pre-trained MobileNet version 2, which what this means is we just drop the classification head. And how do we tell the model, or how do you tell it in code that you drop the classification head? You write include top is equal to false, and weights are your ImageNet weights. Your input shape is 160 cross 160, which we had defined earlier. 160 cross 160 cross 3 for the 3-channel inputs. Then I think we will be having a global average pooling layer. Yeah, we have that as well. Anyway, so after this, what we will be doing is we'll be iterating over the datasets one by one to get each feature batch. Then we'll be extracting the features, and initially we'll be setting the base model or trainable as false. What it means is our entire architecture, which we have just got from a MobileNet, all those weights, we won't be modifying them at all. Let's look at the number of weights which we would be training. So we have about 2.2 million parameters. None of them are trainable, but we do need a classification head, because otherwise how are we planning to actually classify between a cat and a dog? So we actually will be using a global average pooling layer to convert this 5 cross 5 cross 1280 into a 120 cross 1, because I'm sorry, 1280 cross 1 cross 1280. And here you see 32 cross 1280 because you have 32 images. So 32 times 1280. And after that, you basically have a single dense neuron. What it means is just a single neuron. It will take as input all these 120 neurons inputs and give you one output. If any of this is not clear, see what happened till now is we had this shape 5 cross 5 cross 1280. This 5 cross 5 cross 1280 becomes 32 cross 1280 after applying this global average pooling. From that, this 32 cross 1280 is because you have 32 feature maps from the 32 input images, and 1280 is your number of neurons. So emanating from 1280 neurons, you have 1280 arrows, right? All of those 1280 arrows are going into one single neuron. And that one single neuron is your output neuron, which is called your prediction layer. Basically, it's just a layer with one neuron. So now we'll basically build a model, which is we have defined the input as cf.keras.input. We are using the functional API from Keras here. We have already defined the data augmentation as two layers. One of them was the rescaling and one of them was the flipping. I'm sorry, it's not rescaling. Let me just go back to it. Let's click on this. The augmentation. Here you see that we had these two layers. One of them was for the flipping and one of them was the random rotation. Next, we had the pre-processing, the input stage in which we rescaled the values. Next, we had the base model, which is this enormous layer, enormous neural network which we got from MobileNet. Then we have the global average pooling layer to share, to average out the weights and to correct the dimension shapes as well. And finally, we had no, before that they also added a dropout layer, and I think it would be mentioned here that dropout only works during training and not during testing. So what this means is that when we are training randomly, one to about 20% of the weights would be turned off, so all of them would be zero. This actually prevents your neural network from overfitting. Then finally, we have the prediction layer, which is the outputs. Why is this plural? Because although you have just one output, but for 32 images, you have 32 outputs. That's why it's outputs and not output. And finally, we have the model. We initially set a base learning rate as 0.0001. This is also the base learning rate recommended by the Adam paper, if any of you are reading research papers as well. Uh, Till now, we are actually talking more about development and not much about explainability. And after this demo completes, we have another demo, and there we'll be talking a bit about how these classification networks works or what happens under the hood, and also a bit about how we can improve our understanding of them and a few research papers as well. So anyway, we have set the optimizer as cf.keras.optimizers.atom. We compile a model and we have set the loss as a binary cross entropy, which basically means the similarity between the pixels has to be high. And we have a matrix called accuracy. We can also have a matrix called loss. And then you can, as we train the model, I'll actually start training the model because otherwise it might take some time and we can discuss by then. I think it won't take very long. It would take just a few, maybe up to 3-4 minutes to train this model. So till then, yeah, let's continue the discussion from here. So we set our optimizer, we defined how the loss function would work, we defined the metrics, and why do we have two training variables? Why do we have two trainable variables? Because one of them is our output neuron and one of them is the global average pooling layer. You can, instead of len, you can also write print. Then you can actually see the training variables as well. I'll run that cell as soon as this training ends. Till then, I'll see if you have any questions in the chat section. All right, it seems there are no. Okay, Shubhangi has a question. What is the difference between data cleaning and data rescaling? Sure. So imagine that in your cats versus dogs data set, there are also some very blurred images of cats and dogs which cannot be used, which even a human cannot identify. So feeding them into your neural network would just make the accuracy very bad. It won't help the neural network learn anything. So we should remove them from the training data set. Also, it might have giraffes or cars and other stuff in the training data set, which also do not help. So we will try to remove all those unusable data points in our dataset, and removing them by hand or maybe by an algorithm is the data cleaning part. And data rescaling is that your neural network uses something called gradient descent to get the best weights for the neural network, and it won't work very well if one range of inputs, if for one input your range is 0 to 255, another input your range is 0 to 1, maybe another input it's minus 10 to plus 10. So everything, all the inputs has to be rescaled to maybe minus 1 to 1 or 0 to 1 or some small but definitive range. For example, here we had rescaled to minus 1 to plus 1 because that's what the authors of MobileNet or the developers of MobileNet did. But we could as well have also rescaled to 0 to 1 if we had been training our own neural network. And then we were supposed to actually print this trainable variables thing. Let's go ahead and do this. So here which we see is that we have two variables. One of them is the global average cooling layer, which has 1280 units. So you see the first tree and the last tree here, and this dot here. We also have something called uh, a bias unit for that a perceptron, the last perceptron, the output perceptron, and that has just one value, which is 0.017. That would just be added to the output of the perceptron. All right, so fortunately our training has completed and we can see the training curve now. As we see, our training and the validation losses have decreased quite smoothly. Excuse me. So here it's actually written that why the validation metrics are actually always better than the training metrics. That's because of the batch normalization and the dropout layers, which don't work during validation and testing as well. Anyway, now that we have gotten an accuracy, let's look at the accuracy. So we got 97.22% accuracy on our validation data set, which is actually remarkable because we did not really do much training. We just trained those 1280 weights. That's it. And it took about 3 minutes. And we solved a problem which was a Kaggle problem in 2016 with just a few lines of code. So that definitely tells us how far ahead we have come, but we have a bit more to go as well. So with fine tuning, we can reach even greater levels of accuracy. So let's call the base model as trainable as true. So what this means is that the entire huge model that we had with 2.2 million parameters, we set the entire thing as true. So right now we will be training the entire thing. But obviously that's not possible. So you'll see, we actually write for layer.basemodel.layers. What this means is that the first 100 layers will be set to false again. So apparently, the mobile net architecture had 154 layers, out of which we set the first 100 layers to be non-trainable, and then the remaining 54 layers to be trainable. This is what this code does, this part of code does. And we will be training this once again. I actually started the training quickly so that we don't waste any time. We're running a little short on time right now. But no worries. Right now we see that we have 1.8 million parameters to be trained on every epoch. And we have about 396,000 parameters to be trained, to not be trained, sorry. And you see that the trainable variables has become 56. That's because the 54 layers which we are training and the 2 layers from the previous, which we already had. So it's 2 plus 54, which is 56. All right. We'll definitely get an accuracy over 97% by this fine tuning. By the way, all this code is freely available on TensorFlow docs. So if you want to run this at your own leisure, you can just search on Google TensorFlow transfer learning cats versus dogs, and you can run this code at your own pace as well. If you have any questions, you can always drop them in the chat section, or you can actually also contact me after the workshop. Uh, I'll drop my social media plug links after the workshop as well. So already the training has almost completed, and we see that we have definitely reached about 99% accuracy, 98.77% accuracy, which is pretty great. Even the fine tuning did not really take much time. And you see this vertical green line here. What it means is that the initial part was without fine tuning, and this remaining part is after fine tuning. Also, I actually feel that the green line should be a little bit afterwards, because if you really zoom in, you would notice that up to the 10th epoch, it was being trained with uh, it was being trained without fine tuning. So maybe there is a little bit of a distortion. Maybe it's because of my screen resolution. Maybe it's, I'm not really sure what's giving rise to this distortion, but the green line might be more suitable, maybe a little bit to the right. But that's not anything we need to worry about right now. Let's look at the test accuracy, which can be very simply calculated with a model.evaluate call on the test dataset. So that gives us about 98.1% test accuracy. So our model has not overfitted. It has gone well, it has performed really well. So you see the predictions and the actual labels here. This gives you a pretty visual view of comparing that how well our model is performing, and it seems that out of the images, all of them have been correctly predicted. All right. So with this, we come to an end of the transfer learning demo. All right. Shubhangi has asked how much minimum percentage of accuracy is acceptable. That's a really relativistic question. Like for cats versus dogs, if you're solving this problem in today's world, we would be expecting at least 97% or 95% accuracy. But maybe if you're predicting something which is more of a research topic, maybe diabetic retinopathy, even getting 85% accuracy with good confidence metrics would be really good. Again, if your problem is very new and you are the first person to be working on it, then, and if suppose it's a binary classification problem, but it's a very unique binary classification problem, very challenging from a research perspective, then even maybe 65% would be very good, because randomly choosing in binary classification will give you 50% accuracy rate. So even if you're getting 60% accuracy, it means that your model is showing some levels of intelligence. So that might be very good as well. So it's really relative to your problem and the current literature in that field. All right. So now let's swiftly move on to the next demonstration, where I'll explain to you how the neural network works at every single layer and what it sees at every single layer. And preferably, if we have time, I might also give you some research topics and ideas about computer vision at the end. All right, so I'll stop this. All right, so again, I hope my screen is visible. Um,
Yeah, your screen is visible.
all right. So you see this, we have opened this notebook which talks about layer-wise feature activation map. I'll quickly come down to it, but don't really get surprised by the term. It's not that big. What it means is that each single layer of the neural network, it has these feature maps which are being trained, right? These weights, which we call in the neural network, these are actually feature maps. So each feature map is actually looking at a particular part of the image, and we can actually develop heat maps from these and have even more advanced visualization or explainability metrics like CAM, GradCAM, GradCAM++, which we won't be covering today. But today what I'll be showing you is some code which you can easily like copy paste or like fit into your own machine learning pipelines to understand why your model is predicting something in a particular way or why it's not performing very well. So here we are actually going to use Lawrence Moroney's data set as well, called horse versus humans. In this data set, all the horses are real horses and all the humans are computer generated humans, like no real human face was used for this training. Again, we'll be using the flow from directory methods as well. So in train horse names, we basically do an os.list directory to get all the horse names like horse 1, horse 2, etc. And we can count how many of those horses we have in our dataset, which shows that the train consists of 500 horses and 527 humans. And the test set consists of 128 horses and humans. Uh, we'll import TensorFlow and we'll basically define our model. So in the previous example, we had used the functional API, but now we will be using the sequential API. So here we write tf.cadence.models the sequential, and whatever layer we want to define, we can do inside this. And the goal of this demonstration is not to get a very high accuracy. We actually would be getting a very low accuracy because we have just like three convolution max pooling layers. And then we have one flatten. What flatten does is say you have one square matrix. The cells are numbered 1, 2, 3, then 4, 5, 6, and then 7, 8, 9. What flatten will do is it will convert the entire matrix to one single array. Imagine it's a vector 1, 2, 3, 4, 5, 6, 7, 8, 9. All those numbers in that order. And then we have a dense architecture. So there are 512 units in that. So every single unit in the first layer would be connected to every single unit in the second layer. So the first unit would be connected. Imagine we have the 3 units in the first layer and 4 units in the second layer. So the first unit in the first layer will be connected to 4 units in the second layer. Again, similarly, the second will be connected to the 4 units, and thus you will have 12 connections. So then we have another dense connection, which is activated by the sigmoid activation function, which we just saw. This is how the neural architecture looks like. Let's go ahead and train this. Here we are using RMS prop as optimizer. You can also use Adam, and I have actually used Adam with this example, and it works pretty well as well. I swiftly went over all these parts where the train generator is created, the validation generator is created, because we have already discussed how flow from directory works, because you have defined the keyword for the horse and the human, and you are just passing the directory for the model to automatically infer whether it's a horse or a human. Alright, so I think this training will take about another 1 minute. And we have got a decent accuracy as well, about 85% accuracy. So that's pretty okay. I mean, that's actually more than what we usually get. But don't be fooled by the accuracy here, because it could just be like whatever batch it's looking at, it's getting lucky and it's getting high accuracy. That might not even be the true accuracy on a test data set, because I have used this architecture a lot before and it does not really work very well with this less amount of training. But the reason we are demonstrating with a small architecture is because if you have a bigger architecture, those feature maps would become very complicated to analyze. You would very quickly understand what I'm talking about. Uh, for this example, we already have a test data set, but I'll also upload some images from my own computer so that it's even more, what do you call it? Um, explainable, it's easier to understand, etc. Okay, so let me upload the images which I downloaded a while back from Google. These files and all right. So I have four images of horses and 4 images of humans. All of them I have labeled as horse 1, horse 2, horse 3, and horse 4, and human 1, human 2, human 3, and human 4. All right. It seems like unfortunately I downloaded an image of a horse which is 15 megabytes in size. Oh, wait, how big is this image? Let me look at it. No, it's just 1.5 MBs, but the issue is actually that they are not expecting users to be uploading this big files. They're expecting users to be uploading small files to Colab. So the upload speed is a little bit less. But anyway, we have reached human 4 as well. And we are done. Now basically I have written some code here so that you can visualize the images. First, we have the 4 horses, and next we have the 4 humans. The reason I chose these horses are also very unique because the first one is obviously a horse with its tongue out, which looks a bit funny, but you do not expect to have this sort of horses in the training dataset. The second image is a normal horse on a field. The third image is a black stallion, and the fourth image has a human sitting or riding this horse. The human images are also interesting. The first is a normal human. The second is 4 people who are partying, maybe celebrating Diwali with crackers or something. The third image is that of a woman in a village who is cooking something on a stove. And the fourth image is a woman sitting in a gym with a dumbbell next to her. So let's see how a neural network predicts these outputs. Also, this is the code which we use to actually randomly choose, randomly choose an image from all the horse files and all the human files. I mean, all the horse files from test. Um, yeah, from the training and all the human files from the testing. So moving on, predict. Where is the code? Yeah. So let's first of all go ahead and try to predict for all of them. So horse 1, horse 2 are predicted correctly. Horse 3 has been classified as a human. That's a black stallion because apparently the network has not seen this sort of an image before. And horse 4 is again correctly classified. But amongst the humans, only the first human is correctly classified, and all the human 2, 3, and 4 are mislabeled. So basically, what this algorithm is trying to do, what we are now going to do, is we're trying to see which part, at which part the neural network is actually focusing wrongly on which parts of the image. How do I do this? All right, let's first of all look at this horse tree, which is actually a horse but classified as a human. So basically, we'll just write a horse tree. So we see that this is classified as a human, and now we can see the layer-wise feature activation map as well for this. And this is the reason I actually did not choose a bigger neural network, because already you see that the images in the last layer are very small, and demonstrating it would be difficult. Wait a second, let me share my entire screen with you so that the process becomes faster. All right, so what you see right now on the screen is what's there in the first neural layer. That's the convolutional layer, and that has 16 units. So you will see 16 horses on your screen. Let me zoom in a bit so that you can get a better look at it. And you see that the network is looking at pretty much the right places only. Now let's see what it does in the last layer. Even then, it looks like, the network is pretty much looking at the right places. This is actually a good sign, and I have not actually come across this before, across this example before, because whenever the network mislabels, it always looks at the wrong places. But here it seems like it's looking at the right places, but unfortunately the weights are such that for this particular example it did not work. Definitely, if we give such more examples of black horses, the network will correct itself. Let's consider another example now. Maybe the human tree was wrongly classified as well. Let's consider that one right now. Human tree. So that's a woman with the soap in the village, and she is classified as a horse. And let's look at why that's happening. I'll explain the layer-wise feature activation map code as well after this example. So you see that from the very first, the woman's shape has been pretty much ignored. Maybe the filters were not very good. One of the neurons manages to at least have a good border around the woman, but that's still very vague. And as we move towards the end, it should be just background noise. Yeah, and this is pretty much just background noise. And why background noise actually indicates more of horse, I can give you a good reason about that. Because horses are usually present in maybe with places with a lot of trees or places with a jungle or something like that in the background, and those have a lot of rough edges. So the neural network basically learns that whenever there is a lot of plants or trees in the background, it's a horse. This is actually one of the pitfalls of computer vision, used to be a pitfall of computer vision, or these techniques especially, is that you are thinking that you are building a horse versus human classifier. However, what the network is actually doing is it's trying to detect trees in the background. So if there are trees in the background, it will call the image as a horse. If there are no trees in the background, it will call the image as a human, irrespective of what's actually at the forefront. So that's the reason using this layer-wise feature activation map and seeing if the image is actually focusing on the background or on the foreground can give you a better understanding of if your neural network is actually a horse versus human classifier, or is it just looking at the background. All right, we have a lot of interesting questions which I'll take on in a while. Let me first of all finish this demonstration. All right, so the last part of it is where I'll actually explain to you how this code works. We zoom out a bit. Yeah. So what we do is we basically pick up each layer one by one, and as we are putting in the image, we see what sort of change is happening in the image as it passes through the layer. How do we type this and write this in terms of code? We say layer.output, which is what you get after an image has been passed through a layer, and we get the successive outputs. And now for the successive outputs, you create a tf.keras.models.model, which is just Keras' way of saying that, okay, this is a model's weights. And then you reshape them once again to 1 comma to get this shape 1 comma 150 cross 150 cross 3. And again, you rescale them by 255 to rescale the values between 0 and 1. For example, imagine your values are from 0 to 255. If you divide all the values by 255, your output range would be 0 by 255 to 255 by 255, which is 0 to 1. Then the successive feature maps, you use a visualization model to predict that. And we have something called feature map.shape of -1, which is basically the shape's last value. In Python, whenever you write -1 in a list, you basically get the shape of the last value. So it should be 32 in this case because we have that many number of features. It actually has to be dynamically calculated because some layers will have 16 feature maps, some will have 32. Let me go and show you this from the architecture. So here we have 16, 16, 32, 32, and 64, 64. So that's why this has to be calculated with a feature map.shape -1. Here you have some values, like those values from 0 to 1 are multiplied by 64. Then you are adding 126 to it. These values you can also slightly change. For example, see the outputs which I have on my screen. If, for example, in place of 64, if I write 78, and if I basically run the same cell, it will still work, but some of the values will go out of range, some values will become more sharper. So 64 and 126 was just something which we found to work. There's no such hard and fast rule that you have to use the same values as well. All this code does is it makes it look more visually presentable. Alright, so now we have seen enough of our own testing images. Now let's actually randomly select an image from the data set and try to test that. So here we see that we have a human, and as I said, all the humans in the data set are CGI humans, so this is what she looks like. And let's look at where the image is, what the model is predicting at each particular input. So here I'm selecting the 3 layers which I want to look into. This is the first layer, and as you see, the human has been quite clearly segregated from the rest of the image. So this definitely means that the network is going on in the right path. Again, here there has been some blurring, and but still the figure of the human is very clearly visible. And in the last, there are 64 neurons in this layer, and once again you can see the face and the hand very clearly. So, and there's no background noise, like you don't see bright speckles in the background which might indicate that it's a horse, so that's not there as well. So it's classifying pretty well. Now let's try to select another random horse. Maybe this time we'll get a horse. Yeah, we got a horse this time. Basically, we're randomly selecting, so we not know which time we'll get a horse or which time we get a human. Also, it's actually correctly predicted as a horse, and this is what the neural network sees at each layer. You can also see this code. You can find this code on my GitHub repository. I'll share the link as well after the workshop. So I won't be going in and zooming into the value and each layer one by one, because it's clearly visible that the shape of the horse has been segregated in the first layer. And in the last layer, the horse's legs are again very clearly visible. Let's zoom into that. So you see the horse's legs are very, very brightly colored in these neurons here, where I'm moving my cursor. All right, so I think this demo went well. Right now, let's take some questions from the audience. So, which data augmentation methodology is preferred for object recognition? Depends on what sort of data you are trying to recognize. For example, if you are trying to recognize numbers, please do not flip the numbers. For example, maybe okay, although you asked for object recognition, I talk about both classification and object recognition together. For classification, imagine you have a lot of sixes in your dataset and nines, and you're randomly flipping the dataset vertically as well. In that case, your labels don't mean anything, because a 6 when reversed looks like a 9. So you have to be aware of these features in your dataset. Usually, the common pre-processing techniques would involve flipping the image horizontally. You flip the image vertically only if you know that your test dataset might also include such images. Then you can increase the sharpness, you can decrease the sharpness, increase the contrast. You always have something called adaptive histogram equalization, or AHE method. You can also use something called clip level adaptive histogram equalization, which we use for our diabetic retinopathy project. Also, you can try out something like An image has three channels, red, green, and blue, right? But all of the channels won't include the same level of information or be equally useful for your project. For example, for diabetic retinopathy, we found out that using just the green channel and not averaging the red, green, and blue or taking a grayscale image out of it actually worked better. So we worked just with the green channel of the image. So these are some of the ways. Also, you can give some rotation, maybe up to 20 degrees, 30, 40 degrees. You can give some rotation. You can crop the images a bit. So the image is not always centered. For example, although in your data set, all your horses and humans are centered, in an actual image, the horse might be only in the top left and the remaining image might be that of a lake, or maybe there's a lot of sky background or something. So you have to be prepared for all those, and hence we have to consider all those techniques during data augmentation. Shubhangi Singh said, I use a heat map but cannot see my data values on it. How do I solve this issue? I did not really get the question. I think what you mean to say is that you got a separate heat map based. So you have a square with heat maps on it, but the actual image is not. So in Matplotlib, you can already do this with superimposing the heat map on top of your original image, so that you can get which part of your image the heat map is representing, and that would help you analyze like okay, whichever parts are red, the network is looking at more, and whichever parts are blue, the network is kind of ignoring. And that's what you would get when using a cam or gradcam based approach, which I'll be discussing now. Although there is no live demo for it, we don't have the time for that as well. So swiftly, I'll go back to my demonstration. So we already discussed transfer learning, and computer vision in machine and computer vision research currently has a few approaches by which we can talk about explainability in a network. We have something called uncertainty maps, we have visual explanation, and we have saliency maps as well. So here you see about original image, guided GradCam plus plus. These are all previous approaches, the guided GradCam approaches. And then we have something called GradCam and GradCam plus plus. So GradCam is something which I think Shuhangi was trying to talk about. So you have the heat maps in the image, but you do not have the original image on this. So what you can do is you can take this image and you can superimpose it on the original image to get back the a better representation. Still, even if you have the images side by side, you can pretty much understand that. Imagine you see those. Let's consider the second row on my screen. So we have two black and white dogs on my screen, and you can see that the network is actually paying a lot of attention towards the face of the dogs. And that is actually what networks do. Like in the higher level of the neural networks, it would be looking for features like where the dog's face is. You might also notice that okay, even I missed. There are not actually two dogs. There are three dogs in the image, and the neural network also missed the third dog in the GradCam approach. But in the GradCam plus plus, which worked a bit better, it it looked at all the three dogs and their bodies pretty well. Moving on. Uh, all efforts in explainability can be categorized broadly into three methods: post hoc versus anti hoc, which means that post hoc methods are only uh, used after the entire model has been trained. Anti hoc methods are used when the model is training, or even in both, like when the model is training and after that. A model agnostic versus model dependent. Some explainability methods work only with a particular model, whereas other methods work with all models. So that's what the term model agnostic versus model dependent would mean. And global versus local, which means that whether it's only for a specific part of the image, or if it's giving you an overall understanding or a good understanding for the entire image, if it's looking at the entire image and coming to the conclusion. Uh, Definitely. Yeah, I have mentioned the too long didn't read for the slides as well, because we spoke a lot about explainability. My past demo was completely about trying to explain a neural network and what it was doing. But why is it even required? Because, well, if you have an image and your neural network is classifying something, so why do you need this? The reasons could be for human trust, system debugging, and legal compliance. For example, if your car goes and crashes into a human being and kills them, everyone asks, right, who is to be punished? So for those conditions, explainability would definitely be something which we have to look at. There is no monolithic agreed upon definition of explainable AI, and explainability and interpretability comes at a cost, both in terms of time of training and accuracy as well. If you consider models which give you lower accuracy, like maybe decision trees or something, you can get very, very high levels of interpretability. But if you want your model to be very accurate, your interpretability might suffer, which is usually the case with very deep neural networks, especially those with skip connections, etc. And human-based evaluation is essential. So we have a sort of architecture called HITL, human in the loop, in which the machine does everything, but the human can at any time stop and change the part of the car, or maybe in your autopilot in your planes. It's an HITL implementation. So although the plane flies by itself, but a pilot is there. So in case of turbulence or in case of situations which the model might not have seen before, the pilot can take over. RT has asked what is type of layer in a neural network. I think I think what she's trying to ask is that what are different types of layers? Like we have convolutional layers. So a convolutional layer does a certain operation to create a feature map. Similarly, we have pooling layers. So imagine we have a pooling layer on a feature map. What that would do is, imagine we have a 3 cross 3 pooling layer. So it will pick the first 3 cross 3 number of cells from your image or from the previous feature map, and it will, for max pooling, it will select the maximum value of those 9 values and put them in a new cell. Again, it will stride over, and then from the next 3 cross 3 block, it will select another maximum value and then place it in the next value for your output. So that's how max pooling works. For average pooling, you select the average of these 9 values. For minimum pooling, you select the minimum of those 9 values. You can also have various kernel sizes, like I spoke about 3 cross 3. It could also be 5 cross 5, 7 cross 7, etc. It could also be even, like it could be 4 cross 4 or 5, 6 cross 6. But usually in computer vision, we always use odd values so that we have a central line of separation. That's just that's not a rule. It's just something which we usually do. So to answer your question, what are the different types of layers? We have convolutional layers, max pooling layers, minimum pooling, average pooling, dropout, batch normalization, uh, average, global average pooling, and in fact, we have many other layers. You can go back to the documentation for Keras or TensorFlow, and you can just type for layers, and it will give you a long list which has about 40 to 50 types of layers. All right. So these were the two live demos which we had in today's presentation, and some resources as well. I also would refer you to this paper, A Bag of Tricks for Image Classification with Convolutional Neural Networks. This is written by AWS, Tong Hei and all. So I love their paper. It's actually a very old paper from December 2018, but they actually discuss a lot of very interesting tricks. For example, they discuss learning rate warm-up. So you might already know about learning rate decay, but you might not know about learning rate warm-up. So imagine you start with a bigger learning rate and think that with as our model trains, I'll keep decreasing the learning rate. But in the initial layers of the neural network, your neural network training is not very stable. So learning rate warm-up would be useful in those scenarios. Then we have something called low precision training and a lot more. I won't go into details in this paper, but the reason I recommend this paper for everyone is that it's very easy to read. Unlike some papers which are very mathematically heavy, which have a lot of equations, this one is not like that. You can pretty much read it. It's common English, so any of you can read this and understand every single thing that's written in this paper. It's very easy to read, very friendly, and super useful. So with this, I come to an end of my presentation and would love to take your questions right now.
Guys, I think we have reached the end of the session. If you guys have any doubts, you can ask in the comment section. We can wait 3 more minutes.
Sure. Also, these are the links which I said I'll share at the end of my presentation. You can reach out to me on LinkedIn, Twitter, email, or my GitHub. So, I mean, GitHub is only for if you have any uh, suggestions, like if you want to make a pull request or if you want to improve certain parts of my code. Otherwise, if you want to ask any questions, please reach me on my LinkedIn or email.
Guys, we have posted the feedback form on the comment section. Guys, everyone can give a feedback to this session. Guys, and I'm also at the Discord link. If anyone want to ask further questions in future, you guys can join the Discord link, and kindly everyone give us great feedback. Yeah, I think we have reached end of the session. Uh, okay, can we wind up the session?
Sure. And
Okay.
I would like to thank everyone from GirlScript for organizing the event and calling me for this presentation. It was such a pleasure to work with all of you. And
Yeah,
also to the audience for being so amazing, asking questions and being active.
okay, that's great. Shubham, do you want to ask any question, Shubham? Everything good? We can wind up.
Yeah, sure, sure. We can wind up here. Thank you guys
Yeah.
for joining our live, and we will be very pleased to having you all. Hi, yeah. Are you
Shubham, I think
getting
your
audible
mic is
about?
not very clear.
Your voice is something fishy, like thing.
Robotic.
Yeah, I think we can wind up
The
the we have
mic is
reached.
not very clear. All right.
Yeah.
Thank you, everyone.
Okay. Thank you, everyone. Okay.
All right.
Yeah.
Bye-bye.
Finally, just join to our Discord channel for the further thing, and we have a session for tomorrow also. Oh, okay, guys. I think we can end the session. Okay, guys. Tomorrow we have a session on about the LinkedIn, how to increase your LinkedIn profile strategies. Lot of stuff about the LinkedIn are tomorrow coming up. Oh, I think everyone can reach to tomorrow event also. Just join our link Discord channel. You guys will get the updates of our GirlScript channel. It's soon. Yeah. Bye for everyone. We are doing this.